Hello and welcome to today's lecture on MOS inverters. Today we shall discuss about the switching characteristics of MOS inverters. Of course, before that we shall be discussing about the various types of MOS inverters that we have discussed in the last two lectures, and we shall have some kind of comparison. And here is the agenda of today's lecture. This is primarily on switching characteristics. After giving a brief introduction, we shall discuss about the resistor estimation. You will see that different types of resistors are present in a VLSI circuit, and that resistor will lead to some delay, because you know that resistance and capacitance, these two are the parameters which are responsible for the delay of a circuit. So, we shall discuss about the resistance estimation, how we can estimate the resistor, then capacitance estimation, then we shall discuss about the delay time estimation in terms of the resistors and capacitors, then how we can reduce the delay, various techniques which you can adopt to reduce the delay, that we shall discuss, and another technique we shall use to measure the delay with the help of ring oscillator. So, these are the topics we shall cover, but before that let us have a comparison of the MOS inverters. So, in the last two lectures we have discussed different types of inverters, MOS inverters that you can realize. We have seen the inverter is realized with a NMOS transistor as the pull down device, and various types of pull up devices like resistor, NMOS depletion mode transistor, NMOS enhancement mode transistor, pseudo NMOS transistor, I mean inverter, that is actually P type MOS transistor that is used as pull up device, then CMOS inverter. So, these are the various types of inverters we have discussed, and these are the four parameters which we shall compare. One is your VLO. VLO is essentially the low level output voltage of the inverter. That means, when the output is supposed to be 0 volt, low level, then whatever voltage it provides, that is represented as VLO. And we can see for all the inverters except CMOS, the V low is weak. The reason for that is very clear from these diagrams. You can see here this is the case for depletion mode transistor as pull up, this is the case for enhancement mode NMOS transistor as pull up, and this is the case where PMOS transistor is used as pull up, and this is finally the CMOS using PMOS transistor as pull up. So, in all the cases we find the V low is above 0 level here, even for pseudo NMOS, but in case of CMOS it is you are getting 0 for 0 level. So, that is the reason why you can see the only for CMOS the low level is strong. Strong means you are getting ground level output when the low level voltage is 0. For all other cases it is weak. The reason is that you are getting little higher than 0 volt at the output. Similarly, we can compare the high level output which is strong for all the cases except for NMOS enhancement type inverter. I mean, where the pull up device used is NMOS enhancement type. For all other cases it is strong. Strong means we are getting VDD, we shall be getting VDD at the output. As you can see from these diagrams, we are getting VDD when we are using NMOS depletion type transistor as pull up, we are getting VDD when PMOS transistor is used as pull up, and in case of CMOS also we are getting VDD at the output. But in case of NMOS enhancement type transistor as pull up, we are getting VDD minus VTN as the high level. So, we can see here except for NMOS enhancement type inverter, I mean where enhancement type transistor is used as pull up device, we get strong VDD. Then consider the parameter, we have considered the parameter noise margin. So, we have seen noise margin is poor for low for resistor type inverter, where resistor is used as pull up, or when NMOS transistor is used as pull up, or when NMOS enhancement type is used as pull up, or for pseudo NMOS device is used. For all the cases, noise margin is poor for low level. The reason for that we have already seen, because we are getting a output which is above the ground level. Obviously, noise margin will be inferior for low level. But for CMOS we are getting good noise margin, because you know that we get low level output here. So, noise margin is good for CMOS, but we find that noise margin is bad both for low and high level in case of when the NMOS enhancement type device is used as pull up. We know that the noise margin, let me emphasize the point here. We know that this is the VOH that is being generated by the device, and similarly VOL that is generated by the device at the output, say inverter is producing that. On the other hand, we are expecting VIL at the output, as long as it does not exceed that limit, then we are getting we shall be considering that low level as low level. Similarly, VIH is the high level output, minimum high level output that is expected. So, this is the noise margin at high level, and this is the noise margin at low level. So, this particular region. Now, ideally, as you know, in case of ideal situation, VOH should be equal to VDD, VOL should be equal to 0 volt. Similarly, VIH and VIL should be equal to VDD by 2. That means, transition should take place in the middle, and both of them will be at VDD by 2. So, in that case your noise margin for both low and high level will be equal to noise margin low will be equal to noise margin high, both will be equal to VDD by 2. But we have seen that is not the case. So, noise in reality noise margin low is defined as the VOH minimum minus VIH minimum. Similarly, sorry, this is your NMH. Similarly, that N noise margin low will be equal to VIL minus the maximum minus VOL maximum. So, these are the actual noise margin, and obviously it deviates from the ideal situation that we have already discussed, and we find that noise margin is good only for CMOS. Then coming to the power dissipation, the fourth important parameter is power. We find that power dissipation, there is static power dissipation when the output is low for all the cases except for CMOS. So, we have seen that in all the cases both the transistors are on, here in case of this inverter with enhancement mode transistor is pull up, or with depletion mode transistor is pull up, or enhancement mode transistor is pull up, or PMOS transistor is pull up. In all the cases both the transistors are on when the output level is low or when the input is high level, and as a consequence there will be static power dissipation and and obviously they are not suitable for low power applications. But in case of CMOS we have seen both for low level and for high level only one of the two transistors is on, and as a consequence there is no static current flow, and obviously there is no power dissipation when the input output is low or when the output is high. Of course, as we have seen in case of CMOS, there is power dissipation when input changes from 0 to high. So, during the transition or from high to low. So, that part will be there, but that will be dependent on how quickly the transitions occur. Later on we shall discuss about it in more detail, but as such there is no static power dissipation in CMOS except during transition. And as a consequence we find that the power dissipation in CMOS is low. And from these comparisons what conclusion we can make? We find that all the 4 parameters that we have discussed is good for CMOS, and that is the reason why CMOS is the technology of choice, and CMOS is used for all present day VLSI circuit realization, and obviously they are most suitable for low power application because of low power dissipation. Okay. So, with this comparative study, let us move to our main topic, that is your switching characteristics of MOS inverters. So, we know that MOS transistors are realized by fabricating conducting regions of diffusion, polysilicon and metal separated by insulating layers of silicon dioxide, that we have already studied in the first lecture itself. And as we know, each layer has both a resistance and a capacitance that affect the behavior and performance of circuits realized using the MOS transistors. And obviously, these conducting layers will have finite resistance and also capacitance associated with them, and that will affect the switching characteristics. Switching characteristics means when the input is changing from maybe from low to high or high to low, output is also changing from high to low or low to high. So, that those will be affected because of the resistance and capacitances. Of course, they too have inductance which however is small enough to be neglected. That means, the inductance value is too small, and obviously they contribute very little in the operation of the switching characteristics. I mean, they will not affect much the switching characteristics of the devices, and that is the reason why we shall ignore the inductive part of the different components that we shall be using. We shall be mainly restricting to capacitance and resistances of the devices. And obviously, to start with, we shall discuss about simple models of resistors and capacitors that can be used to model delay characteristics of CMOS inverter. So, we see now we shall focus only on CMOS inverter or CMOS complex circuits. We shall not discuss about any other types of inverters that we have discussed so far. Okay. Coming to resistance estimation, let us consider a rectangular slab of conducting material. Let me draw it here. Let us consider a rectangular slab of material. So, this is a rectangular slab I have drawn, and we have one conductor on this side, another conductor in on this side for taking interconnection. That means, you want to measure the resistance of this slab, and by attaching a maybe multimeter or some other device at these two ends. Now, the physical dimensions are shown here. L is the length of the slab, and W is the width of the slab, and T is the thickness of the slab. And in addition to this, it has got another very important parameter in the context of resistance estimation, that is your resistivity. Resistivity is equal to rho, and rho defines the resistivity of the material that we will be using, and obviously this resistivity will vary from material to material. We have seen we shall be using different types of conducting material like diffusion region, polysilicon, metal and so on, and obviously their resistivity will different for different material. And so, this if we consider this point A and this point B, this resistance between these two terminals A and B will be equal to rho L by OL by T into W. So, this is the resistivity of the of this particular conductor between these two. Now, this can be also represented by rho L by A. Area is essentially the area of the device, that means area will be equal to T into W, that is the area, and L is the length. So, based on this we can this can be also represented by another very important in another way, say it is actually L area L by W. So, let us represent in terms of rho by T into L by W. Now, let us consider a situation where L is equal to W, that means length is equal to width. In that case it is a rectangle, I mean it is a square. So, whenever it is a square, that square can be 1 nanometer by 1 nanometer or 1 millimeter by 1 millimeter or 1 meter by 1 millimeter, it does not matter, because as long as these two are same they will cancel out, and this will be equal to rho by T. And when L is equal to W, then whenever this is the situation, we define a parameter known as RS. RS is equal to rho by T, and unit is ohms per square. So, ohms per square is the unit of the seat resistance. This is called the seat resistance of the material. Quite often the resistivity of a conducting layer is specified in terms of the seat resistance. The reason for that is, using this parameter you can calculate the resistance for a given dimension. For example, you are given a, say this is the, let us assume we are considering say we know that, let us assume that L by W is equal to say 4. Let us assume L by W is equal to 4. That means, width L by W length by width is equal to 4. Then what will be the resistance between A and B? And obviously, in that case we can express it in terms of R A B will be equal to 4 into R S when L by W is equal to 4. So, you can see we can express the resistance of that particular layer in terms of the seat resistance, if we know the length and width of the device of a particular material. So, in terms of this seat resistance, we can calculate the resistance of a conducting material, and these are the typical values of seat resistance for different conducting material which are used for the realization of MOS transistors. We know that we shall be using metal for taking interconnection. We can see the seat resistance, that is ohms per square, is, I mean obviously for metal it will be very small because it is a extremely good conductor. Metal essentially is aluminum and typical value is 0.07, and obviously it will have some minimum and maximum value, because the thickness, resistivity of aluminum is fixed, but thickness will vary whenever you do the fabrication. So, it will vary from fabrication technology to fabrication technology. As a consequence, the seat resistance will vary, and for a particular fabrication technology this is given. Similarly, for diffusion layers for N type and as well as for P type, the seat resistance is typically 25 ohms per square, minimum is 10 ohms per square and maximum is 100 ohms per square. Again, that thickness of diffusion, that the depth of penetration of the diffusion layer will vary from fabrication technology to fabrication technology, that will lead to different set resistance for the diffusion layer. Similarly, silicide, that is also used in the fabrication, and you can see it has got some resistance, not very high resistance, 3 ohms typically, but polysilicon, as you can see, which is used for interconnection over short distances. So, polysilicon is used as interconnecting material for connecting, say, from drain to gate of one transistor, from drain of one gate transistor to gate of another transistors, and so on for short distances, and their resistances are the set resistances given here. On the other hand, the N channel and P channel, that resistance is quite high. That typical value of resistance of the N channel is 10 to the power 4 ohms per square for N channel, and for P channel it is still more because of lower mobility of holes, that is 2.5 into 10 to the power 4 ohms per square. So, you see these are the typical values of set resistances for different types of conducting materials, and in fact, here for a particular process technology, 180 nanometer process technology, that previous one was for little higher process technology, maybe 5 micron or so, and this one is for 180 nanometer. So, it is still old, but you can see the values are little different. So, for the diffusion layers, you can have two types of diffusion layer. One is silicided, another is no silicide. So, in that case you can see the set resistance will vary from 3 to 10 ohms without silicide, and when no silicide, then 50 to 200 ohms. For polysilicon, when it is silicided, it is 3 to ohms again, and for polysilicon. So, you can see diffusion and polysilicon, when silicided, they are giving more or less the same resistance. So, is the diffusion layer and polysilicon layer are also providing more or less similar kind of resistances. However, the different types of metal layers are used. In a present day VLSI technology, a number of layers of metal is used, and as a consequence their thicknesses and their the T value of T is different, and as a consequence we find their that set resistance is varying from 0.08 to 0.02, and metal 1, metal 2, metal 3, metal 4, metal 5 and metal 6. So, these are the typical set resistances in 180 nanometer process, and these information can be used for the calculation of delay. Later on we shall discuss about it. Coming to another very important parameter, that is your capacitance estimation. We find that load capacitance at the output of a CMOS gate is a sum of the following capacitances. If you consider a CMOS inverter, then at the output you will face these three capacitances. Gate capacitance is essentially, I believe I have a diagram. Let me draw a diagram. Say this is an inverter, this will be connected to maybe another stage of inverter or some more complex circuit. So, you see here it will face the gate capacitance of the next stage. So, gate capacitance of the next stage, that is what is being shown here, gate capacitance of the next stage. Then diffusion capacitance. So, diffusion capacitance is essentially the capacitance for this particular stage. We shall show it in more detail in subsequent slides. Then routing capacitances, because you have to take interconnection from the output to the input of the next stage, and these interconnections will have some capacitances. So, you can see the capacitances for different materials is shown here. Gate to channel, that will actually characterize the gate capacitance, 4 into 10 to the power minus 4 picofarad per micron square, and considering this as the standard and everything is normalized with respect to this, then the diffusion layer has got 1/4 the capacitance, compared to gate channel. So, that means gate to channel has the maximum capacitance compared to other regions. So, diffusion layer has 1/4 capacitance picofarad per micron square, then polysilicon has 0.1 1/10 of that of the gate capacitance. Metal has still lower capacitance, 0.3 into 10 to the power minus 4 picofarad per micron square, metal 2 0.2 into 10 to the power minus 4 picofarad per micron square. Then metal 2 to metal layer, whenever the VLSI fabrication is done in a multiple layers, nowadays the VLSI fabrication is done in multiple layers. So, there will be one metal layer and below there can be another metal layer. So, that will also lead to some capacitance. Metal 2 to metal 0.4 into 10 to the power minus 4. So, you see the capacitance is little high compared to that polysilicon. Then metal 2 to poly 0.074, here it is very small. So, we find these are the different types of capacitances that you will encounter whenever you realize a circuit, VLSI circuit. And coming to the gate capacitance, we find that MOS capacitor depends, MOS capacitance we have seen typical value is 4 into 10 to the power minus 4, but actually it is not fixed. Dynamically the gate capacitance will change depending on in which mode it is. We have already seen the MOS transistors will be in the accumulation stage initially when the gate voltage is small, less than the threshold voltage. So, in that case that channel region will be filled up with the carriers of the original device, that means substrate. For example, whenever if you are using p type substrate, holes will be there. So, presence of holes will be there, and as a consequence in the accumulation mode capacitance will be quite high, because capacitance will be dependent on, say suppose this is your silicon dioxide and here it is polysilicon. I am drawing a channel region, then this is the substrate. So, this is the substrate and this is the substrate, and initially as you have seen there will be holes present here. So, the thickness of the conductor will be the thickness of the silicon dioxide. So, if we plot the capacitance as it moves from accumulation to depletion to that inversion, as you increase the VDS, then the capacitance will change, and particularly when it reaches the depletion region, this part will be devoid of any charge carrier, there will be no charge carrier. So, it will be depleted. So, effectively that will increase the thickness of this silicon, the insulator. So, as a consequence in the depletion region the capacitance is less, but again when inversion layer is created there will be electrons here. So, again thickness will reduce and capacitance will be more. So, what I am trying to say here, the capacitance value of the gate region is not fixed, it depends on the gate voltage that you are applying, and because of the different values of gate voltages the device moves from one mode to another mode, accumulation to depletion to inversion mode, and accordingly the gate capacitance will change. And gate capacitance can be estimated as epsilon 0, that is the permittivity of the free space, and epsilon INS insulator, that is silicon dioxide, typical value of this is 3.9 as you have seen, and A is the area of the that length into width, and this is the thickness of the silicon dioxide. So, this is the typical value of gate capacitance, but again we shall see that particularly this thickness will change, and that will lead to different values of gate capacitance as it goes from one mode to another mode. Coming to various parasitic capacitances, we find that different types of parasitic capacitances. For example, CGD and CGS. So, here you have got CGD here, gate to drain and gate to source. These CGD and CGS are essentially because of overlapping of the gate region on the source and drain regions, on the diffusion regions, and as a consequence this will have some capacitance CGS and CGD due to the gate overlap with the diffusion regions. Similarly, CDB, here you have got CDB drain to body and source to body. These capacitances, because this part will be, there will be depletion region here, there will be depletion region here as well, and this will probably lead to some capacitance, and as you know this is N plus and this is P. So, there is a diode and this they will, it will have some capacitance, that is your CDB and CSB. So, these two are voltage dependent junction capacitances, because they are, as we have seen, they are reverse bias diodes, and depending on the reverse bias voltage their capacitances will vary, and as a consequence they are voltage dependent junction capacitances. Then C out is another capacitance that you will encounter whenever you interconnect a inverter to other parts of the circuits, that is essentially the distributed capacitances due to interconnection. C out is not shown here, I shall see in the next diagram. Similarly, CGN and CGP are due to the thin oxide capacitances over the gate area. So, here in the gate area this is your CGB, CGN and CGB, actually CGB is a generalized form of capacitance. In case of N type NMOS transistor, this will be CGP, because this body will be, this substrate will be P type, and for P type transistor this will be CGN, because it will be N type substrate. So, CGN and CGP are due to thin oxide capacitance over the gate area of the NMOS and PMOS transistor respectively. So, these are the various capacitances you will encounter, and this is the simplified model that we can make from this. So, here what we have shown, this is an inverter with its associated capacitances. So, this C interconnect is that interconnect capacitances that I mentioned, and here are the CGP, CGN it is encountering. So, diffusion these capacitances it will encounter, this output will encounter. What we can do, we can see that the effective load capacitance CL is essentially sum total of CDGN, CDGP, CDBN, CDBP, C interconnect, CGN and CGP, because we have so many capacitances associated with it, and these capacitances can be lumped together for the sake of simplicity to define a single capacitance CL, load capacitance. So, later on we shall be referring to a single capacitance, that is CL, load capacitance, but essentially it comprises many capacitances, gate capacitance, then to body capacitances, interconnect capacitances and so on, which I have shown in this diagram. So, let us assume this is our simplified model for estimating the delay characteristics of an inverter. So, one inverter is driving another inverter with a load capacitance CL. So, this is our simplified model. So, how do you define delay? Delay of a gate. So, here we have removed the other gate, because we have the representative load capacitance CL, which has taken into consideration the gate capacitances of the next stage. So, how do you define delay? You see, normally what you do, you apply an input V in and it produces a output, a device. Now, that input, we can assume that the input is changing quickly, here also it is changing quickly, that means step input. That means the switching times, rise time and fall time of the input is 0, but ideally this will not be so. That means later on you will see this will be, there will be some finite, it will take some finite time to change from 0 to VDD to, this is your VDD and this is 0 volt and this is a 0 level for the output. And as the input of an inverter is changing from VDD to 0, output will change from 0 to VDD, and obviously this output will change after the delay time. So, here we can say this is where the input has changed. We can consider the middle point of the output, I mean input, as the reference. With reference to that, it is changing from VDD to 0. Here it will change from 0 to VDD. It will not, we have seen the characteristics. So, it will change, the capacitor has to be charged. So, it will have a nature like this. So, we can take the middle point as the to define the delay time. So, delay time for, that means TP high to low and TP low to high we can draw. So, TP high to low, this is essentially the TP low to high. So, TP low to high is, this is your T0 and this is your T1. So, this is TP low to high is T0 T1 minus T0. Similarly, here the output we may say that here also it does not change quickly. So, let us assume this is the nature of the input, and as a consequence here also it will change like this, and we can consider the middle point and this point as the this point as the reference. This is your T2 and this is your T3. So, this is equal to high to low time is your T3 minus T2. So, this is the typical time for transition from high to low, this is the transition from low to high. So, these are the two times we can measure, and then later on we shall see that this low to high and high to low times are not same. We have already seen there is some asymmetric behavior of the inverters. The pull up transistor resistance can be different from the pull down transistor resistance, unless we explicitly design the circuit. If they are of the same dimension, their resistances will be different. That will lead to different rise time and fall times. As a consequence, what we do, we measure the take the average, that is your TD. TD is equal to TP high to low plus TP low to high by 2. That is defined as the delay time. So, this average value is considered to be delay time of the device. Question is, how do we really measure this delay time? And to measure the delay time, we can have a very simplified model. What is that model? For an inverter, say whenever we are, let us consider this case when it is charging from, I mean it is going from, input is going from low to high. That means we have your there is a that pull up device is on, which is responsible for the for this change from 0 to high, low to high. So, in that case what we can do, we can model it this way, as if a this is your VDD and this is your load capacitance CL, and here there is a switch, and in this particular case whenever it is switching from low to high, this capacitor is charging from low to high, then this switch is off. This is representing the pull down device and this is representing the pull up device. You may be asking why you have represented this device as pull up device. The reason for that is, in this particular case, as you can see, during the period it is changing from low to high, output is essentially that input to the you know that this particular device, let me draw it, an inverter. Let me draw an inverter, that will make it clear. So, here we have got a capacitance connected to ground CL. Now, it is charging through this path, it is charging. Now, it is charging from 0 to VDD. So, what is the state of this device? That time what input you have applied to it? When it is output, when the input is VDD. So, input is VDD is applied here, and it has switched to 0. That means, the most of the time you can see the input is varying from 0 to VDD, and this output is changing from 0 to VDD. That means, the voltage across this device is varying from 0 to VDD by 2. So, since it is varying from VDD by 2, we may assume that this transistor is in saturation, and as you know, when a transistor is in saturation, the current remains constant, and that is the reason why the pull up device has been approximated as a constant current source in this particular case. So, when it is charging, it is assumed to be a constant current source, which is responsible for charging the device. Similarly, you know, whenever we are discharging it, we shall consider this, that the pull up transistor is off and we have a constant current source which is discharging this capacitor CL. CL is getting discharged through this path and through this constant current source. So, and we shall assume that both the transistors are in saturation when this charging and discharging is taking place. So, this is VDD and this is ground, and as a consequence we can write down the expression for current DSN in this particular case will be equal to beta n by 2 into VGS minus VT square. We know that. So, this is charging from 0 to VDD, and obviously since it is discharging through a linear current path, it is discharging from 0 to VDD to, in this case, VDD to VDD by 2, and initially it was VDD, then VDD by 2. So, in this case we can say that time will be equal to VDD minus VDD by 2 will be equal to beta n by 2 CL into VGS minus VT square into T1, I mean that time that we have shown, this whenever it is this particular, it is high to low. So, T2 minus T3 minus T2, T3 minus T2. So, this is your TP high to low. So, this if we substitute here, we shall, this is VDD by 2, this 2 will cancel out, and we shall be having an expression for TP high to low, that is equal to VDD by beta n, this will go to at the denominator, into CL by, this will go up, CL by VDD minus VTN square. So, this is the expression that you will get. So, this is the expression for Tp high to low. Similarly, we can find out the value for the other one, that Tp low to high. What is the difference between these two? Difference is, in case of PMOS transistor it is NMOS transistor, otherwise it is different, it is same. So, we can write down the expression for Tp low to high is equal to CL by beta p, beta is Kw, beta p is equal to Kp Wp by Lp into 1 by same, here we can write VDD minus VTP square. Okay. So, this is the expression that we can write. Now, What is the delay time? Td is equal to Tp low to high plus Tp high to low by 2. So, this will be equal to, by substituting beta p in place of beta p, is equal to Kp Wp by Lp as we know, and similarly for beta n is equal to Kn Wn by Ln. What the expression that we shall get will be equal to Ln by Kn Wn plus Lp by Kp and Wp into Cl by Vdd into 1 minus Vt by Vdd square. This is the expression that we are getting ultimately for the delay time. You may be asking how you have got this figure. Actually, Vdd was at the numerator. What we have done, we have taken out the Vdd outside. So, it has become Vdd minus Vtp or Vdd minus Vtn, and one Vdd has cancelled out, and here we are getting Vdd minus Vtp by Vt. So, what does this expression tells us? This tells us about various parameters on which the delay will depend. Obviously, delay will be more if the length of the devices is more. That means it will take longer time, resistance will be more, it will take longer time for the electrons to move from one end to the other end. Similarly, if the width is more, then also delay will be less, and there is a parameter here, mobility of electrons and holes. That part also will be Kp and Kn has got those parameters, mobility of electrons and mobility of holes. They will also be responsible to define the delay. But those are fixed parameters on which, I mean, of course, length and width we can change, we cannot change Kn or Kp. But what kind of dependence it has got on Cl? Actually, we can say, we can discuss in more detail here, say how delay can be reduced, on what parameters it has got dependence. So, the width of the MOS transistors can be increased to reduce the delay, and this particular technique is known as gate sizing. Later on we shall discuss about it in more details. Then load capacitance, we have seen there is a parameter called load capacitance on which there is strong dependence, and as a consequence the load capacitance can be reduced to reduce delay. And how it has been done? As we go from one technology generation to the next technology generation, the dimension of the devices is reduced. That effectively reduces the capacitances, and actually Moore's law has flourished based on this. That means capacitances have reduced, the performance has increased, delay has reduced, then the device can operate at higher and higher frequency. So, and last factor is delay can also be reduced by increasing the supply voltage Vdd. We have seen in this expression Vdd is present here. So, by increasing Vdd, the delay can be reduced, but unfortunately as you increase the supply voltage, the power dissipation increases, because power dissipation is proportional to Vdd square. That is the reason why normally we do not want to use the increase the supply voltage, rather the supply voltage has to be reduced, but we have to see how the performance can be maintained even when the supply voltage is reduced. That is the challenge of the low power design. Now, coming to this part of the expression, this is very interesting. We can see here, this is 1 minus Vt by Vdd square, it is in the denominator. Now, if as you reduce Vdd, whenever you go from one technology generation to next technology generation, you can also reduce Vt in the same ratio, and as a consequence the Vt by Vdd ratio is maintained to maintain the same performance. But if you do not do that, if you simply reduce the supply voltage, without reducing the threshold voltage, what can happen? You will see this value will keep on reducing, and I mean this VT, the VDD is reduced. So, this value is increasing, will be increasing, and whenever VT will become very close to VDD, that time this will be very close to 1. So, when the denominator is I mean this particular part is very close to 1, this will have a very small value. So, and the square of that will have still smaller value, and then the delay will be very large. That means, when the supply voltage is close to the threshold voltage, delay increases dramatically. So, that is the reason why we should not use supply voltage close to the threshold voltage. Normally, typical value of VT is in the range of 0.2 VDD to 0.5 VDD. We can see this is the safe operating range. That means, we can get reasonable performance whenever the threshold voltage is kept in that range. So, that is the reason why in my last lecture I was mentioning that the CMOS inverter will keep on functioning even when the supply voltage is equal to threshold voltage or less than threshold voltage, but delay will be very large. Okay. Now, another question arises, how delay can be measured? How delay can be measured? So, delay value is very small. It is in the for present day technology, it is fraction of nanosecond. You know, the devices are it is operating clock frequencies few gigahertz, and the consequence the delay will be few nanosecond or fraction of nanosecond. How do you measure it? We cannot measure it with the help of an oscilloscope. So, a special type of circuit is made known as ring oscillator, and ring oscillator is fabricated using the devices of that generation, inverters of that generation, and then the delay is estimated. How? Let us see. Question is, what is a ring oscillator? A ring oscillator can be realized with the help of several inverters in this form. That means, what you will do to realize a ring oscillator, we shall use odd number of inverters 3, 5, say 3, and then we shall apply this output to this input. So, that means 3 inverters connected back to back, and this will form a ring oscillator. That means, value of n, number of inverters present, has to be odd. Then it will form an oscillator. What is the function of an oscillator? It will oscillate and generate clock. Then the time period of the clock can be measured. Question is, on what factor the time period depends. Let us see from this diagram. As you can see here, I have plotted the voltage of 3 different points. This is the 3 inverters connected to realize a ring oscillator, point A, point B, point C. So, point A is the input of the first inverter, point B is the input of the second inverter, point C is the input of the third inverter. So, here assuming that it will oscillate. So, here say this is the delay time, this one between one line and another line, this is the delay time. So, when at this point it is changing from 0 to VDD, next stage will change from VDD to 0 after the delay time, next stage here. So, here it will delay, that means after the delay time it will switch from high to low. So, here it has changed from low to high, here it has changed from high to low. Similarly, this will lead to a transition of this inverter from low to high. So, B at output C, at point C will have a transition from low to high after delay time. So, in this way, and again this C is now this output, at the output of C it is essentially point A. So, point A will switch now from high to low, because it has changed from low to high. So, this output of this inverter will change from high to low. So, in this way we can see I have plotted several waveforms, and we can see this is the time period, and that will be true for at point A, point B or point C, at all the points. So, this total time, this is the time period of the clock that has been generated with the help of this ring oscillator, and this particular time period is equal to the rise time and fall time TPHL1, that is the first stage, plus TP low to high of stage 2, TP high to low of stage 3, then again TP low to high of stage 1, and so on. So, this total time comprises these these times, and they can be clubbed. So, TPL1 and TPHL1 and TPHL2, these two can be combined, and this is equal to 2D. As we know, TPHL1 plus TPLH1 by 2 is equal to TD. So, this is equal to TD, this is equal to TD, this is another TD, 2 TD. So, we have got 6 TD. So, 6 TD is equal to 2 into 3 TD, and since n is the number of stages here, this is 2 into 3 into TD. So, we can say that the time period is equal to 2 and n is the number of stages of the inverters into tau d, that is the delay time of a particular stage. Now, instead of t, we can express in terms of frequency of oscillation as well. So, f is equal to 1 by 2 n T D. So, whenever we want to measure this delay, what we can do, we can extend the time, increase the time period by increasing the value of n. Typically, we can have say as large as 101 inverters or 151 inverters, and using that we shall form a ring oscillators, not 3 or 5. So, when we have got large number of inverters and they are connected to back, the delay time will be easily measurable with the help of the equipment that is available at our disposal. So, to measure the delay time, we use ring oscillator having large number of stages, maybe 101 or 151 or so. That is how whenever a new generation technology is introduced, its delay time is measured to characterize the new generation technology. Okay. So, we have seen how delay can be measured. Now, it is time to summarize what we have discussed. We have compared different types of inverter, the performance of different inverters, and we have seen CMOS is the inverter of choice. We have introduced the concept of series resistance. We have introduced various types of capacitances that you encounter in a VLSI circuits, and you have discussed how delay time can be estimated, and I have highlighted how the delay time can be reduced by controlling different parameters. Finally, I have discussed the use of ring oscillator for delay measurement. Okay. So, with this we have come to the end of today's lecture. In the next lecture, we shall discuss how large capacitances can be driven by inverters. Thank you.